This is a part of my PhD work. I recently joined PhD on January. And we had just started the work, so what we are doing is we are just presenting the results so far we developed. And we are still working on further results. You already know that about the columns, which are structural members subjected to vertical loads, constantly vertical loads. And buckling is the main failure that can happen to column. It's a developed branch, and our industry is in what happens when there is a crack in the column. This is not a novel idea in our mind. Already there are so many publications in this field, even from the late 1960s, when these persons started with experimental work on this. Then they started working on analytical. Then you had work on FEM analysis. But all of the works were focusing on what happens to the load acting and what will the effect or what is the maximum load the system can bear. Then works developed onto extended to FEM analysis, then to composites, and even to civil structures also. The work is fine. So this give us some. This gives some energy to work on this, and we fixed our objective that apart from this loading, what are the different geometric and loading parameters that can influence the seat and how? That's our interest. So our aim is to capture the variation of the seat for these parameters. The first one is the eccentricity of the loading. You can see that the load is happening here with an eccentricity from the midway. Then what happens when we change the position of the crack? Here the crack is positioned here. I can vary the position from bottom to top anywhere. Then what happens when we change the aspect ratio, or so-called slender ratio? Then what happens with respect to the cracking? So that is our interest. All these four parameters are independent of each other. Now the methodology, we define the geometry. We have the fixed base. It's fixed with the 0.9 meter. Load is also fixed, 1 kilonewton. All others are independent parameters. We change the aspect ratio. It is defined as height by base. We changed it from 1 to 20 with an increment of 1. Then relative crack length, there is A, crack length divided by the base. We changed it from 0.05 to 0.95 or 96 cents. Then eccentricity, we changed from 0 to 1. That is 0 means loading at this point, 1 means loading at 8. Now crack position also we changed from bottom to the top. And we are investigating one by one. And before that, about the machine, we did our analysis on ANSYS APDL. And since we are focusing on the crack tip, we followed the 8-node quadrilateral element. But to capture the SIF singularity, we used specialized Barroso elements on the inner circle, and the outer circles we have 8-node quadrilateral elements. And this is about our mesh. To do the mesh convergence, we varied two parameters. One is what is the radius of this inner element. Another one, how many elements we can have around the circumference. So we did the mesh convergence. We plotted a normalized table for different circumferential divisions. And we fixed our work with this point, focusing on this point, where the circumferential division around the crack tip is 8, and the F rho we fixed with A by 5. So this is our point. And about the block-less element, we fixed it as 1.5 times the F rho. Starting with the effect of each parameter, the first one is the aspect ratio, that is defined as height by base. So for that, we plotted the variation of the SIF, especially the K1, with the relative crack length, for different eccentricities. We did for the same we did for different aspect ratio. Randomly choose an aspect ratio. And what is the surprising one, we found out that all the graphs are the same. So what we did is we plotted the variation of SIF with respect to aspect ratio from 0 to 20. And it's a straight line, so that shows that aspect ratio is invariant of, sorry, SIF is invariant of aspect ratio. Then to investigate what is the influence of the crack length, we can use the same graph here. See, when the crack length is increasing from 0 to 1, then we can find that the SIF is varying from an entity towards the infinite, either negative infinity or positive infinity. So that shows the singularity. Except from eccentricity equal to 1, all are showing to moving towards negative infinity. So we can conclude that as A by B, the related crack length move towards 1. The effort or SIF is moving towards singularity. So those are our findings for the two parameters, aspect ratio and crack length. Then in the same graph, one more thing is we notice that for some of these eccentric values, the SIF is on a crossing fraction. So crossing mode. For other, we have a positive SIF, opening SIF, and crossing mode. So do they? Is there any relation for that which governs in which eccentricity we will get a positive and in which eccentricity we will get negative SIF? For that, we did the basic analysis from a mathematical point of view. We did the loading here, and this is my stress distribution. We have negative stress on this one and positive stress here. And the crack will be open only when we have this red one. And that shows that when the compressive and the tensile stress are greater than 0, we have opening crack, and that is achieved only when we have the eccentricity greater than or equal to 1 by 3. So we ended up with this equation, and we cross-checked our relation with one of odd journals in 1969 by Okamura, and they also stated the same. Again, if you are so interested, we can cross-check this one here. For the first 3 eccentric values, which are 0.1, 0.2, and 0.3, all the SIF are negative. But for later one, from 0.4 itself, we are getting positive SIF. Now, to investigate the effect of eccentricity on this, we have a huge set of data, so we randomly plotted all these one and connected them with a straight line. So it reveals that when eccentricity is increasing, SIF is also increasing linearly. It's a linear trend. So that we can finalize that SIF eccentricity is linearly dependent. This is the same one. The same thing we can happen for a non-crack body also. Now the next one is the crack position. That is where we are placing the crack. Is it at the bottom, or at the mid, or at the top, or somewhere in it? Incorporate with the singularity. And we fixed the order of singularity as 1 by 5 by trial error. You can see it here. For n is equal to 1, it shows singularity, and 2 also shows that. But n is equal to 1.5, we can get a final answer. So we fixed our order of singularity as 1.5. Then to fix the polynomial, we got that the 4th order polynomial shows the best fit. So we fixed it with the degree 4. And this polynomial is a function of relative crack length A by B. And we again worked on all these coefficients of Pi. And it surprisingly shows that it's a linear variation with eccentricity. So what we can find is that the final analytical expression for the normalized SIF is a function of relative crack length and eccentricity. Now, to quantify how much the error we have in our feet, we plotted the percentage error, that is defined as the difference of F1 value we got from FEM analysis and feet divided by the FEM analysis. And it shows that it's almost a constant like this, except at some points it is going up. So this one is an enlarged view of this selected region, and we can say that it's almost the error is almost in the region of -2 to 1. We didn't stop our work with K1. We worked on K2 also, but K2 values are so much less compared to K1, so we didn't have more focus on this. But these K2 results are all fine, and it also shows the same trend like K1 also. When you plot it for eccentricity ratio, it shows that it's a linear trend, and again for the related crack lines, we can see that at the bottom and at the top, sorry, at the lower related crack line or the top, there is 0 or otherwise it's varying. And these works are on the way. We also have a more mixed ratio. It shows that K2 is only a small fraction of K1, it's only spanning over minus 0.1 to 0.1. So it's just a negligible value. So what we did is we concluded our work as it says that more or less pure mode 1. What are the conclusions we have? We fixed the aspect ratio. We found out that it is not influencing the signal. The positioning of the crack at the lowermost or at the topmost will influence the signal. Otherwise, it is not influencing. Then about the crack length, it is significantly depends on the crack length as we expected. Then eccentricity, as it increases, crack length also increases linearly, like in the case of an uncracked body. Yeah. So those are our conclusion, and we are planning to extend our work to much more in T2 region, and also we are planning to extend our work for impact. So that's all. I'd like to thank the organizers of the INCAM for giving this opportunity, then to my great Professor Surendra, to my institute for fundings, and to all my friends and colleagues. Okay. Thank you. If you have any questions, I can answer that up to my knowledge.
And the speaker, any questions? Is there any question in the audience?
A1 value you had it shown until the end. I think they were trying to meet at some point. A1. Yes.
Yeah.
But for A2, if you go to A2, it's, yeah. So they are able to converge. So why is that happening?
That's we are still working on that. We got some more surprising results in this case.
No, but surprising is actually the cable part when you were not able to get to that final. You haven't reported that at least. It seems it's all converging to some point.
Yeah.
But you didn't actually. But here you are able to.
Yeah, we did it only up to point some 95, sir. Same thing we did for K1 also.
Okay.
Somewhere up to point 95. We can see the crack length only up to that. You know that it will sort of break.
That's the crack position, right?
Yeah,
X-axis is crack position.
Crack position, so we did up to point 95. The same thing for K1.
Can this problem be done analytically, like without FEM?
Yeah, we are working on that to validate all of
Like
it.
for example, you had this 1969 paper, right?
Yeah.
That once that is done, what would be the usefulness of doing the FEM of that?
Because they are not worried about what is the position of the crack. They didn't read about that one. They just focused on what is the maximum load that the system can bear. All the works were constrained for that. But our